Uh, I'm going to explain on the buck boost regulator. So this buck boost regulator is the combination of the buck and the boost regulator. So this regulator has advantage, or it has a capability to step down the output voltage or step up the output voltage. So this is the circuit diagram of the uh, buck boost regulator or the buck boost converter. You have input voltage DC source Vs connected in series with the switch S. We have inductor here and the diode in this direction, and the capacitor and the load. So load can be any type, RLC or RLE. Now in order to analyze the circuit, we are dividing it into two modes. Mode 1, when your switch S is closed. So when this switch is closed, so that duration is from 0 to alpha t. So this alpha is our duty cycle, where that alpha can be equated as T on divided by T, or the total time period. Now when your switch S is closed, your diode D will become reverse bias. So after the diode, from this it becomes open circuit, or this is disconnected from the input source voltage. So your circuit becomes only Vs and Vl. So if you apply the KVL, so you will see that your inductor voltage will be equal to the input voltage. And if you want to calculate the output current, we have capacitor current here and IC in this I naught load current. So your capacitor current IC will be negative of I naught. So it's I'm simply applying the KCL at node A. So let's say this one is node A. So this is the condition when your S is closed. So we can calculate your inductor voltage, which is equal to input voltage, and your capacitor current, which is equal to the negative of the output current. So mode 2 is when your switch S is open. So again, that's the duration when when your T is between alpha T to the total time period. So when your S is open here, your input voltage Vs will be isolated, and the active circuit becomes only this much. Now here inductor will act as the source. So initially when your S is closed, if you consider this circuit here, this waveform here, inductor initially it will act as the open circuit, or it will offer very high resistance. So current will flow from minimum or zero, and then if you keep on supplying, then your inductor current will gradually increase like this, and then it will attain maximum. So this is doing the turn on time. Now when you disconnect the input source, so your inductor will act as the source, and the flow of inductor current will be from here, from the bottom, okay, like this, in this direction. Because if it is in this direction, then your diode will be reverse biased, so your circuit will not conduct. Now here we have to calculate your voltage, inductor voltage VL will be equal to, VL will be equal to VO. We simply have to apply the KVL in this case. If you apply the KVL, so you will get your inductor voltage VL is equal to 0. VL is equal to V naught, which is equal to output voltage, and just apply the KCL at this node here. If you apply the KCL at this node, so your capacitor current IC will be equal to negative of inductor current IL plus the output current, like this. Okay, this one is your C. This is not inductor current L. Okay, now next we will see how voltage is being amplified, or how that voltage is being stepped down at the output side. So this relation can be given by the volt second balance. Now for this, the is same as the VL during the turn on time plus VL during the turn off time, which will have to equal to 0. This is same as what we have discussed in the buck and the boost regulator. So VL is given from here, it is Vs, and then turn on time is alpha t plus, and then your VL during the off condition is here VO. So it is VO, and then turn off time is 1 minus alpha t if you write in terms of the duty cycle. Okay, and then if you simplify this one, you'll get your VO will be equal to negative of alpha by 1 minus alpha Vs. So this negative sign indicates how you have taken the sign conventions. Okay, I have taken simply from here plus to minus here, and that's why I got negative alpha minus 1 plus alpha. And similarly, you can also calculate the how current is being step up or step down for the buck boost regulator. So this one can be given by ampere second balance. So same here, the capacitor current during the turn on time plus capacitor current during the turn off time, which we have to equate it to 0. So during turn on time, here we have negative of I naught, then turn on time is alpha t again, and then your IC is negative of IL plus I naught, and then this is doing the 1 minus alpha turn of time is equal to 0. And if we simplify this one, you'll get your inductor current IL will be equal to negative of I naught by 1 minus alpha, or if you're calculating the load current, it will be minus of IL 1 minus alpha. And here negative symbol indicates, okay, your IL is opposing the current, load current I naught. So if you check here, IL is going in opposite direction of the load current. And other important parameters that we have to calculate in the buck boost regulator is like ripple inductor current. So in order to calculate the ripple inductor current, so we have to take VL is equal to Vs, which is the voltage given during the turn on time. Okay, when your S is close. So for VL, current and voltage relation is given by dLi by dt, which is equal to Vs, and di is equal to Vs by L dt. So if we this little mistake here. So this is Vs only. So L, now that this change in current here, if you check this one, okay, that di here, we are talking about inductor current, which we can be written as IL, delta IL, because it changes from IL max to IL min to IL max. So change in that current is given by delta IL, and the change in time dt is from 0 to alpha t, which means we can take it as alpha t. Therefore delta IL by alpha t is equal to Vs, and we are interested in calculating the ripple inductor current, so which we can written as Vs alpha t by L, which can be also further simplified as Vs alpha by Fl, because F is equal to 1 by T. So this is the ripple inductor current for the buck boost regulator. And next, let's also calculate what's the maximum value of the inductor current, IL max, and we have to also calculate the IL min. So if you check from the graph, okay, that we have here, that your inductor current increases like this and then decreases when S is turned on or turned off. When S is on here, okay, when S is on here, so inductor current increases, and when S is closed, inductor's charge stored in inductor is decreasing. So it increases from increase for IL min to IL max here, and here we have IL average. So if we just divide from here to here, it will be delta IL by 2, and from here to here also it's delta IL by 2. So IL max will be equal to now whatever the IL average here, okay, let's keep it as the inductor average current plus delta IL by 2 will give you your maximum inductor current. Now if you want to further simplify, you may replace the value of delta IL here, and okay, and you can also replace the value of IL. I think we got value of IL here, so this is the value of IL. So if you can replace here, so we can simplify this step further. So that's the general or the principal formula to calculate the IL max. And similarly, to calculate the IL minimum, again it is this current, okay, this current. Now in this case, it is, we are talking from here to here, so we have to take minus IL, okay, delta IL by 2. And similarly, if you want to further simplify this one, you may replace IL and delta IL. So these are the maximum and the minimum inductor current that we are looking about, okay. So this actually, that's maximum inductor current is the peak current, okay, the positive peak here, and this one we also consider as a negative peak, but in our case it depends upon from where you start, okay, how you're considering. For example, if you're starting from T0 plus or minus, and then it may start from negative, okay. And then next we have to calculate the source current, okay. Now in order to calculate the source current, we are considering as the ideal converter or the lossless converter, which means your, okay, the source current. So here we have to consider input power is equal to, okay, equal to output current. So this is possible only our regulator is lossless or is ideal case. Now for this, input power can be given by VSIS, and output output power is given by VOIO. So IS is can be written as VOIO by VS. So this is your general very generic formula, and if you want to replace the VO or IO, you may do it, and then we can reduce this formula further. And then similarly, we can also calculate the switch current, whatever the current is passing through the switch. So this switch current is very important to give the rating of the switch. Okay, switch current. So let's represent that switch current as SW. So now if you look into the waveform here, so since we are expecting the DC average current at the output side, and now when switch is turned on, okay, when switch is turned on, we can also expect current is passing through the switch like this, and when switch is turned off, then switch becomes open circuit, no currents pass through it. And then if you look into the circuit diagram that we have discussed here, okay, so when switch is closed, so whatever the input current that we have is given through the switch. And then when S is turned off, okay, when S is turned off or when S is open circuit, so you can see that your diode is conducting, or diode is letting the current to prevails. So in that case, so when S is closed, we can expect that this is your diode current and this is your switch current. So which means is something like when S is turned on, we have this IL, and then it's conducting for, okay, to now this one we have to calculate the average. So if you calculate the average, ISW average for this square wave, you will get T alpha T by T, which is equal to alpha IL. And ISW RMS, if you're going to calculate the ISW or the switch current RMS, so it will be alpha IL. Okay, I'm not showing the steps, there are many hidden steps, so we have to calculate we have to use the formula to calculate the RMS value for the square wave. And similarly for the diode current, ID average is given by IL of 1 minus alpha, and ID RMS is again given by IL of root 1 minus alpha. So since we have discussed this one in the buck and boost regulator, I'm not showing the detailed steps. Now if you look into this values here, the formula here, it's same as the boost converter. So you may check the detailed hidden steps. It's simply as like to calculate the average value for the square wave and the RMS value of the square wave. Here alpha T and T. So we have to consider this waveform. And we have to also calculate the ripple capacitor voltage. In order to calculate that one, so this is the target that we are looking for. So when S is on, we have seen that your capacitor current is equal to negative of load current. So for IC is related like that, dVc by dt equal to negative of I naught, and then we have to dVc is equal to minus I naught of C and dt. We have to integrate to get the value of the ripple voltage, capacitor voltage. Now looking at this, we have seen that so that capacitor voltage, it take place, I mean when it is maximum, okay, it discharge from maximum to, okay, minimum. That's why we have taken from here Vc max as the lower limit, and then we have Vc min as the upper limit. And when it comes to the time t is 0 to alpha t, it's something like this. So let me show you with the capacitor here. Okay, this is the one. If you just plot the graph for this one, initially, now if you are considering at t is equal to 0, your capacitor will not have any charge. So for that, we cannot consider the limit in this case. But what we are considering out here is, we are assuming that initially the capacitor is already charged. When your switch S is closed, your diode is open here. So whatever the output voltage that it shows is because of the capacitor voltage out here. So initially it has maximum charge, and then it is supplying the charge to the output load, and then it is decreasing. That's why you have Vc max and then VC min. So this one we are taking it as upper limit, lower limit, and this one we are taking it as a upper limit. So this is how we are considering out here, VC max and VC min. And then if we integrate this one, we'll get VC min minus VC max is equal to minus I naught of alpha t by C. So this one, actually we have VC max minus VC min is equal to delta VC, but here it is subtracting another other way, so we'll take minus of delta VC is equal to minus of I naught alpha t by C. So this minus minus will get cancelled, so you will have ripple capacitor voltage as alpha I naught by FC. So this is the ripple capacitor voltage that we are looking for. And next we have to calculate the critical value of inductor. Now this is very important to check whether our waveform is, to see whether it is continuous or discontinuous. For example, let's say if this one is for inductor L1 and then this is your zero axis out here, so it's continuous because that current waveform is current is not coming to zero. And let's say for L2, okay, it starts from here, okay, and then it's coming to here 0, and then again it goes on, and then it comes to 0, and then it starts. For this, it acts as a, it gives the discontinuous current. So for that, now you will see at what value of the inductor we can maintain the output current as continuous. Now we have a method for this one. So we have to make the minimum inductor current is set to 0. So your IL formula is given by IL min is given by IL minus delta of IL by 2 is equal to 0. If you substitute the value of IL, okay, IL is equal to minus of I naught 1 minus alpha equal to, okay, now 1 by 2, I'm taking this half outside, and then I'm also substituting the value of delta IL, which is given by alpha Vs by FL. And in order to indicate the critical value of the inductor, I am adding the another the referring point here C, okay, critical value of the inductor. So we can make LC as a subject here, and then if we consider for the resistive load, and then we'll have final value R by 1 minus alpha square divided by 2F. Okay, there are so many steps being removed out here, because if this is our primary formula, I am replacing I naught, okay, is equal to VO by R, and then again this VO is being replaced by alpha minus 1 minus alpha Vs. So if you just replace and calculate, then you will get like this. You will get like this. And so this one is only true if our load is R. If not, we'll have to stick on this general formula. And then next is the critical value of capacitor. For this, we have to again equate VC min is equal to 0, and the value of VC minus delta VC by 2 is equal to 0. Put the value of VC, and then you can substitute a note by, okay, FC. Okay, so this will be your critical value of the capacitor here. So we'll have to make this one as a critical value. Okay, see, now for this, if we are considering, okay, if we are considering the resistive load, we'll have V naught by R. So we can substitute V naught is equal to 1 by 2 alpha I naught in place of I naught, V naught by R, and then we have F, C, C. V naught will get cancelled. Critical capacitive value C is equal to now is alpha by 2FR. So this is the critical value of the capacitor in the buck boost regulator. So these are the explanation that I got, and for detail, the book that I'm referring is Power Electronics by P.S. Bimra and Muhammad H. Rashid. So if you refer these two textbook, it will be more than enough to get the concept, okay, whatever that I have explained out here. So I'm not going in detail because other explanations, it's a similar explanation that we have already covered in the buck and boost regulator. So that's it.